In this video, we're looking at complex numbers in polar form. So some properties that we're going to look at is the modulus and the direction of a complex number z. So the magnitude or modulus or absolute value of the complex number z equals x plus yi is the length of the line segment joining the origin to the point z. It's denoted by z in absolute values, which is absolute value of x plus yi or mod z, and so it's going to be the square root of x squared plus y squared. That, of course, coming from the fact that this makes a right-angled triangle. Our imaginary component is y, our real component is x, so the distance of this line using Pythag is going to be the square root of the sum of the remaining two sides. So find the modulus of the complex number z equals 8 minus 6i. So modulus of z is equal to the square root of x squared plus y squared. So that is going to give us the square root of 8 squared plus 6 squared. This is a 3, 4, 5 triangle, I believe. So if these are 2 times 3 and 4, then our answer is going to be 2 times 5. So this is going to be the square root of 100, which is, of course, 10. So the modulus of z is equal to 8 minus 6i is 10. Example 18. If z equals 4 plus 2i and w equals 7 plus 6i, represent the position of w minus z on an Argand diagram and calculate w minus z, the modulus of that. So on our Argand diagram, we've got 4 plus 2i. So 4 plus 2i is coming out like this. So that's z equals 4 plus 2i. We have w equals 7 plus 6i. So 7 plus 6i is going to come out like that. So if we were to transpose this z coming out here, we'd expect our answer to come out like this. So that's going to be, w minus z. So let's fix that up. So w minus z, we want to come in the opposite direction of z. So instead of transposing it addition-wise, we want to do it subtraction-wise. So that's going to be coming back like this. And so our difference is going to be approximately that. So w take z is equal to 4 plus 2i, sorry, no, that's not true, 7 plus 6i minus 4 plus 2i. So 7 minus 4 is 3, 6i minus 2i is 4i, and so the magnitude of that, or the modulus of that, is going to be the square root of 3 squared plus 4 squared. They're being rather nice today, giving us a bunch of Pythagorean triads, so that's going to be 5. So we can see the distance of this purple line that I've drawn is going to be 5. Okay, next property that we're looking at is the argument of z. So similar to how a vector has direction, a complex number has an argument. So in the figure, their argument of z is theta. So sine of theta gives us, let's break this right angle triangle into opposite and hypotenuse and adjacent. So sine is opposite over hypotenuse, so that's going to be y over the modulus. Cosine of theta is going to be adjacent over the modulus, so that's x over the modulus. And then tan of theta is going to be y on x. So for non-zero z, z has to be non-zero, otherwise we get a division by zero error. An infinite number of arguments of z exist for a given z. So we can just keep adding on 2 n pi, where n is a natural number. Just keep rotating that 360 degrees around and we get a new argument. So because clockwise and anti-clockwise rotations consisting of multiples of 2 pi radians or 360 degrees merely moves p to its original position. To ensure that there is only one value of theta corresponding to z, we refer to the principal value or principal argument. It's noted with a capital A for argz, and that is going to be in the range of negative 180 degrees to 180 degrees. or negative pi to pi. Notice that if you are given the choice between negative 180 and positive 180, you always choose positive 180. That's why we have the square bracket for that one, whereas it's the regular bracket for negative pi, or negative 180 degrees. So, some useful triangles to look at. Sine of 45 is the same as sine of pi on 4. So, I'm going to quickly go through and fill all these out. So, making these triangles, in our first triangle, we've got 45 degrees, which is pi on 4. So that's going to give us 1 on root 2 for both sine of pi on 4 and cosine of pi on 4. And then tan, because it's an isosceles triangle, is going to be 1. Then for pi on 3, which is 60 degrees, we're going to get root 3 on 2. For the sine of pi on 3, cosine of pi on 3 is 1 on 2. Tan of pi on 3 is 1 on root 3. So that's opposite over adjacent. No, sorry, that should be root 3 on 1. So root 3, and then this one's going to be 1 on root 3. Yep. So sine of pi on 6. Yeah, so tan pi on 3 is going to be root 3. Sine of pi on 6, which is 30 degrees, is going to be 1/2. Cosine of pi on 6 is root 3 on 2. And lastly, tan of pi on 6 is 1 on root 3. So opposite over adjacent. Find the argument of z for each of the following intervals between negative pi and pi. So for z, we have arg z is equal to tan inverse of y on x, which is going to be tan inverse of negative root 3 on 1. So in our first quadrant, that's going to be tan of negative 1 of just root 3 on 1. So we're just caring about what it looks like in the first quadrant. Root 3 on 1 is, of course, going to give us pi on 3. But we're not in quadrant 1. We have a negative imaginary component. So we're actually in the fourth quadrant. So instead of being positive pi on 3, we're going to be negative pi on 3. So arg with a capital Z is equal to negative pi on 3. And that is, of course, in the interval of negative pi to pi. For part B, similar process, arg of Z is equal to tan inverse of negative 2 over negative 2 root 3. So that's going to be in the first quadrant, tan inverse of just 1 on root 3. So that's going to be pi on 6. But we're not in the first quadrant. We've got negative imaginary component and negative real component. So that puts us in quadrant 3. So third quadrant. So instead of being pi on 6, so if we were here, that would be pi on 6. We actually want this angle. So we need to add, take pi on 6 away from negative pi. So negative pi, no, not take pi on 6, plus pi on 6. Sorry, because it's going in the anti-clockwise direction. So that would give us negative 5 pi on 6, which is our capital A arg of Z. Example 20, convert each of the following into arguments. So arg of Z is going to equal to 7 pi on 4 take 2 pi. So that's 7 pi on 4 minus, 8 pi on 4. Because we can see 8 pi on 4 is the same as 2 pi. So 7 minus 8 is negative 15 pi on 4. Sorry, 7 minus 8 would give us negative pi. So this will be negative pi on 4, which makes sense because we want it to be between negative pi and pi. So that's our capital A arg of Z for A. Capital A arg of Z for B. We want to take our negative 5 pi on 2, and we want to add 2 pi. So that's going to give us negative 5 pi on 2 plus 8 pi on, 4 pi on 2, which would give us negative pi on 2. And that is between negative pi and pi. Alright, example 21. Find the modulus and argument for each of the following complex numbers. So for a, the modulus of root 3 plus I is going to be the square root of root 3 squared, which is 3, plus 1 squared, so that's going to give us 2. To find the argument of z, that's going to be tan inverse of 1 on root 3, which is going to give us pi on 6, and that is between pi and negative 5, so that is the capital A arg of z. So that's for part A. For part B, we got the modulus of 1 minus root 2i is going to be the square root of 1 squared, which is 1, plus root 2 squared, which is 2, so that's going to give us root 3. And our argument of z is going to be tan inverse of negative root 2 on negative 1, which is going to give us 0.955. So that's negative 2 on negative 1. Now, of course, that is our first quadrant solution. So first quadrant. So because we've got negative real and negative imaginary component, we want to look at our third quadrant, which is going to be negative pi plus 0.955. So if I draw this out, this is what we just found. We want to find this. So this angle we found is the same as that. So we want to add that to our negative pi. Hopefully that helps visualize it. And that is going to give us our capital A arg of z is equal to negative 2.187. And so because we're going from negative pi to pi, it has to be between negative 3.14 and positive 3.14, and that suits that. Okay, so expressing complex numbers in polar form. So cosine of theta is equal to, as we talked about earlier, it's going to be adjacent over hypotenuse, so that's x on modulus z. This is going to be y on modulus z. So we could also call that x on r or y on r, as we've established that r is equal to the modulus of z. So, and theta is then, of course, the argument of z. So if we substitute these values into the point, we're going to get r cosine theta gives us our x coordinate, and r sine theta gives us our imaginary coordinate, our y value. So x plus yi in Cartesian form, we've got r of cosine theta plus I sine theta. Another way that's represented is r cis theta. So cis theta is an abbreviation of cosine theta plus I sine theta. We pronounce it as cis. It's just a shorthand because mathematicians are notoriously lazy. So example 22, express the following in polar form. So our modulus of z is going to be square root of 1 squared plus 1 squared, which is square root of 2. Our argument of z is going to be tan inverse of 1 on negative 1. So our first quadrant solution to that is going to be pi on 4. And so if we have a negative real component and a positive imaginary component, that puts us in the second quadrant. So our second quadrant solution is going to be pi minus pi on 4. So pi minus pi on 4 gives us 3 pi on 4. And so we've got root 2 cis 3 pi on 4 is our value for A. B, on the other hand, is going to give us a modulus of z of square root of 1 squared plus root 3 squared, which is 3. Let's fix up that 3. Okay, I've got a dead spot. Yep, good enough. So that gives us root of 4, which is 2. The argument of z is going to give us tan inverse of root 3 negative over negative 1. So our first quadrant solution is tan inverse of just root 3, which is going to give us pi on 3. But because we've got negative real and negative imaginary, we actually want the fourth quadrant, which means we want negative pi on 3. So therefore, r cis theta is going to be 2 cis negative pi on 3. And last question for this video, express the following in Cartesian form. So we want to expand it into cosine plus I sine theta. So our first one, we've got 3 cosine negative pi on 4 plus 3i sine negative pi on 4. So cosine of pi on 4, that's negative 45 degrees. So because we're negative pi on 4, we're going to be in the fourth quadrant, which means we'll have a negative imaginary and a negative real. So this will be negative 3 times root 2 on 2 plus, minus 3 root 2 on 2i. Okay, and then last one, part B, 5 cis 2 pi on 3, that gives us 5 cosine 2 pi on 3 plus 5i sine 2 pi on 3. So if we consider what 2 pi on 3 is, that's the same as pi on 3 away from the negative x-axis. So if we find what it would be in the first quadrant, we just need to make our real component negative, and that's going to take us over here. So that's like a reflection in the imaginary axis. So we know that our real component is going to be negative. So cosine of pi on 3 is going to give us 1 over root 3, so 5 on root 3. And then this is going to be 5 root 3 on 2. Sorry, that should be 5 times 2 on root 3. So this is going to give us negative 10 root 3 on 3 plus 5 root 3 on 2i. And that's all for this video. Thank you very much.